Hello everybody, I'm Johnny Mac, and today we're going to be talking about binary. So this series is designed for the person with no knowledge of subnetting. So I'm going to break each individual part down of the entire subnetting process into the smallest parts I can find, and then make each video a portion, and that way those of you guys that know some of it can skip the stuff that you already know. And those of you that have absolutely no knowledge of that whatsoever, I won't be skipping anything. So you'll be all set. So hold on to your hats, get your calculators ready, and let's go. Alright, binary actually traces its roots back to 9th century China. And there are some examples of binary even being used in early Egypt. So it's something that's been around for like a bajillion years. So almost all communication that happens inside your computer or other electronics happens in binary. Because when you think about it, if I have an electrical circuit, from point A to point B, what can I send on that circuit? I can't send letters. Letters don't fit on there. I can't send anything other than a pulse of electricity or a pulse of light. So because of that, binary is based on ones and zeros. So I do a pulse of electricity for a 1, and I do no pulse of electricity for a 0. So everything's timed like it'll be like, okay, send me a burst, now send me a burst, now send me a burst. And if I get a burst and I don't get a pulse of electricity, I assume there was a 0 there. And if I get a burst and there was some electricity on the line, then I assume that it was a 1. So that's how all the stuff happens inside your motherboard. So your motherboard looks like this, and again, this is a little older motherboard, but your hard drive used to connect to here, and then there were pathways that went into this memory, and then this is where your RAM was, and then your memory then connected to the CPU. So all the programs on your hard drive, they would start loading files into memory, and then memory would feed it into the CPU. And then once the CPU did its job, it would send stuff to the PCI card, which would then send stuff out to your monitor. So inside your motherboard, there are all these little traces or circuits. And then they would send either electricity or no electricity for ones and zeros. So that's how information is transmitted electronically with ones and zeros. Now these pathways on your motherboard are typically called buses, kind of like a school bus. You know how a school bus would ferry children to and from? Well, a bus would provide information from your hard drive into the memory. So I'm guessing that's where they got the concept. Because these buses, obviously in the way back early days, they were 8 bits. But nowadays we have much larger buses, 256, 512, and even larger. Which means we can send 512 bits of information at every beat of the system clock. And the system clock, might click over 100 times per minute. Well, actually, that's pretty... This stuff all happens almost instantaneously inside your motherboard. So let me pull my foot out of my mouth and let's move on. So again, everything inside your PC, connects on these buses. And the bus connects the CPU to the memory, to the input-output, to the video card, all that stuff. And then information is all transferred in ones and zeros. So remember, very early computers only had 8-bit wide data paths. And the reason for that is 8 bits is a byte, and binary sends everything in bytes. So we send a byte at a time. And that's why these buses are always 8 bits or a multiple of 8 bits wide. You either get an 8-bit, a 16-bit, a 32-bit, 64, 128, 256, that kind of stuff. It's all a multiple of 8 because we have to send an entire bit at a time. I can't just send a byte at a time. I have to send a byte. It's so confusing. So look at it this way. If I was going to send, the letters A, B, and C, through one of the buses. Well, again, we're going to assume this is a very early one. It's only 8 bits wide. And we're going to send a pulse of electricity on this first circuit, and then nothing on all these, and then we're going to do a pulse of electricity on this last circuit. And then we're going to say bam and send that, and then we're going to send another set, and we're going to do a pulse of electricity here and here, and then we're going to send a third set and do a pulse of electricity here, here, and here. And that would be A, B, and C. So it's like bam, send 1, bam, send 2, bam, send 3. Now again, this stuff happens almost instantaneous. Imagine your system clock, I want to say, I don't even have actual numbers, but it beats more than several times per second. So when you think about it, if I have a 512-bit wide data path, I can send 64 bits at a time. So 64 bytes at a time. So, and if my system clock is vibrating at 10 times per second, that's 640 bytes of information per second being transferred on your PC. So again, it for the naked eye, it's almost instantaneous. All right, and I keep screwing this up, but there are bits and then there are bytes. So a bit is a 1 or a 0, and a byte is 8 bits. So a bit is a 1 or a 0, and then a byte is 8 bits. So binary only uses bytes. We send everything in a factor of 8. Now there's also another number called a nibble, and a nibble is 4 bits, and we use that in hexadecimal. So when we get to the hexadecimal video, we'll discuss a nibble. There's also another size called a word size, and a word size is 2 bytes. But we don't use that one in networking. So for now, just focus on bit and byte. A bit is a 1 or a 0, and a byte is 8 bits. Alright, so what does a binary number look like? Remember, it's going to be 8 bits, so 1 bit, 2 bit, 3 bit, 4 bit, 5 bit, 6 bit, 7 bit, 8 bit. And we group those in bytes. Just like we use words, we have letters, and then we have words. The only difference is in binary, there are set size. A bit is always a 1 or a 0, and a byte is always 8 of those bits. So everything is based on the byte. We have bytes, then kilobytes, and megabytes, and gigabytes, and terabytes. There are also other languages that are based on binary, such as hexadecimal that we'll talk about in the next video, and that's where we take that's where we use the nibbles. And there's also what they call ASCII, and basically your keyboard actually works in ASCII. And when you press the A key, it'll actually send a 61 in hex to the computer. Then the computer will take 61 and convert that into A. But again, we'll talk about all this when we get into the hexadecimal num. So binary is the very first, it's the building block. Everything else is based on binary. So you have to understand binary. And luckily for us, it's relatively easy. So to start converting from binary and to figure out what these numbers are, we start with the number 1, and then we double it 7 times to the left, and this creates our number line. And then we use this to translate what the binary digit means. So I start with a 1, and then I double it 7 times. So 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, 32 times 2 is 64, 64 times 2 is 128. So I start with 1 and I double it 1, 2, 3, 4, 5, 6, 7 times. And that gives me my 8 bits. My 8 bits. Alright, so your binary number looks like this. 1001, 1011. So we put our number line at the top. 128, 64, blah, blah, blah. And then all we do is we add the numbers that are above a 1. So I would add 128 because he's above a 1. I would add 16 because that's above a 1. I would add 8 because that's above a 1. I would add 2 and 1. So I would take 128 plus 60 or plus 16 plus 8 plus 2 plus 1. And then I would when I add those numbers up, I would get 155. So the binary equivalent of 1001 1011 would be 155 because I would add 128, 16, 8, 2, and 1. So let me walk through another example. So again, the very first thing I want to do is create a number line, and then I want to add the numbers with the 1 below them. So first, let's convert this. So I got this byte here, 1100, 1100. So now I need to convert that. So first thing I do is I put a number line over the top. So I start on the right with a 1, and I double it 7 times. And then I simply need to add these numbers on the top that are above a 1. So I'm going to add 128, 64, 8, and 4. So 128, 64, 8, and 4 is 204. So 1100, 1100 is 204 in decimal. So 2 easy steps. The first step is create a number line above your byte and make sure everything lines up when you're doing these on paper. These should be on top of each other, on top of each other, on top of each other. If you start skewing your numbers and they're way over to the left and the binary is way over to the right, you start making mistakes. So use as much paper as you need, line the things up all nice and neat like that, and then just count the numbers above a 1. So 128, 64, 8, and 4. You can also do, 1 times 128 is 128, 1 times 64 is 64, 0 times 32 is 0, 0 times 16 is 0, whatever makes sense to you. But for me, it's just easier to say, okay, I just need to count the ones, so I have 128, 64, 8, and 4, and then that becomes 204. All right, so now it's your turn. I want you to convert these two numbers, these two bytes, into decimal format. So 1001, 1001, and then 1100, 1101. So pause the video now and convert those, and then I'll walk through the solution for you in the next couple slides. So pause it now. All right, so 1001, 1001. So again, I write out the byte, and then I put my number line on top of it. I start with 1, double it 7 times, and then I just add the numbers above a 1. So 128, 16, 8. 128, 16, 8 equals 152. So 1001, 1000 is 152 in decimal format. Remember, the numbers that we use, 1, 152, 224, that kind of stuff, that's decimal format. And then binary obviously is ones and zeros. All right, the next one, 1100, 1101. Again, I write out my binary byte. I put my number line on top of it. I start with 1 and I double it 7 times to the left. And then I just count the numbers above a 1. So 128 plus 64 plus 8 plus 4 plus 1. 128, 64, 8, 4, and 1 equals 205. So 1001, 1000, actually that should be a 1 there. 205 in decimal format. All right, now that's the easy part. Now we're going to reverse it. Well, we're going to say, hey, I want to give you the number in decimal, and I want you to convert that into binary. So I'm going to give you 172, and I want you to convert it. Well, you do almost the exact same thing. You start with your number line, and then you ask yourself if the number goes into the number on the number line. So if the answer is yes, it gets a 1, and if the answer is no, it gets a 0. So let me walk through an example for you. So I have 172. So again, I create my number line. I start with 1, double it 7 times to the left. And then I ask myself, does 128 go into 72? If the answer is yes, I put a 1 here. If the answer is no, I put a 0 here. So the answer is yes, so it gets a 1 under it. And then I subtract 128 from 72, and then I move on. So I take 172 and I minus 128, and I get 44 left over. So I put my 1 underneath 128, and then I move on to 64. Does 64 go into 44? Well, the answer is no. So I'm going to place a 0 here. And then I move on. Does 32 go into 44? Well, the answer is yes. So I place a 1 here, and then I subtract 32 from 44 to get the remainder. So I subtract 32 from 44 and find out I have 12 left. I put my 0 and my 1 here. And then does 16 go into 12? Well, my answer is no, so I'm going to put a 0 here. And then this should say 8. So does 8 go into 12? And the answer is yes. So I place a 1 there. And then I need to subtract 8 from 12, and that's going to give me 4 left over. So there's my 0 and my 1. 8 minus 12 is 12 minus 8 is 4. So now I know 4 minus, or does 4 go into 4? Yes, so I'm going to put a 1 here. And then my remainder is going to be 0. Once your remainder is 0, the rest of your numbers are 0. So this is going to be a 1, and then a 0, and a 0. So 172 in decimal is 10101100 in binary. Now, it's a lot harder to show this on the slide. So let me convert this live for you. Alright, so here I have my number line. So now let's convert some numbers. So I'm going to grab the pencil, make this a little bit thicker, and say, hey, let's say I want to do a nice easy number, so I want to convert 224. So what I typically do is I write my number up here, 224, and then I start. Does 128 go into 224? And the answer is yes. If it's a yes, I put a 1. So then I need to take 224 minus 128, and I get 96. Now, does 64 go into the remainder? Does 64 go into 96? The answer is yes. So 96 minus 64 equals 32. Don't laugh at my writing. Does 32 go into the remainder? Yes. And then 32 minus 32 equals 0. And remember, once you have 0 as the remainder, all other numbers must be 0. So 224 is 11010000. Now, for me, it has always helped to do this kind of thing on the top. You know, start with my number and then subtract whatever I subtract and get the whatever the remainder is, and then go to and then subtract that from the next number and get the remainder, and keep working until the remainder is 0. When you get to 1, your remainder, whatever's left, should be 0. If you have extra, you made a mistake. All right, let's do another one. All right, let's do 187. So again, same thing. Does 128 go into 187? And our answer is yes. If it's a yes, we put a 1, and then I need to subtract 187 from 128. And I get 59. So does 64 go into 59? The answer is 0. And then I move on. Does 32 go into 59? The answer is yes, so I put a 1. So 59 minus 32 gives me 27. All right, does 16 go into 27? The answer is yes. So 27 minus 16 equals 11. Does 8 go into 11? The answer is yes. So 11 minus 8 gives me 3. Does 4 go into 3? No. Does 2 go into 3? Yes. That should be just a bit of minus. Equals 1. Does 1 go into 1? Yes. So 1 minus 1 equals 0. So when you get to 1, your remainder should be 0, and that's how you know it's right. So 187 is 10111011 in binary. So again, same thing, just keep answering, you know, does this go into that? Does this go into that? If the answer is yes, you do a 1. If the answer is no, you do a 0. If the answer is yes, you need to subtract that to get the remainder, what's left. If the answer is no, you just move on to the next number. And it helps me, again, immensely if I do it this way all the way across as I'm converting that, so I kind of like know where I'm at. Alright, so we're back, and your turn. So convert these two numbers, 193 and 87. I want you to convert those into binary. So pause the video now and convert those, and then we'll check your answers. Alright, let's see how you did. Now, if you ever want to check your work, you can use the Windows calculator as long as you have Windows 7 or below. If you have Windows 8 or Windows 10, you're having some issues. And let me kind of show you the difference between those two. Alright, in Windows 7 and before, this is what the calculator looks like. And I'm sorry I can't resize this, it doesn't resize. But you can hit Mode and go to Programmer, and then you get a decimal, binary, and hexadecimal conversion. So I can say, hey, what's 193 in decimal, and then click on the binary button, and it'll convert that into binary. So you can check your work with that. Make sure you just don't get lazy. If you just use the calculator to do all your stuff, you won't be able to do it by hand. You won't understand how it works. And when you go to your first job interview and they ask you to convert 224 from binary to decimal, you'll be like, duh, and you won't get the job. So don't be like that. For some reason, I don't know why, but a lot of IT guys in their interview process like to ask you something about subnetting. They'll either ask you to subnet, or they'll ask you how many networks or how many hosts you can have on a subnet, or they'll ask you to convert something from binary to test your understanding, especially for entry-level jobs. So don't get lazy. Make sure you understand the process and can do it on pen and paper, and just use the calculator to check your work. Now, if you're using the Windows 8 calculator, you're going to have issues. So here's the crappy Windows 8 calculator. Again, there's nothing to convert. If I go to scientific, there's no binary that I see there anywhere. And if I go to converter, it just does. Oh, maybe I can convert this from volume to data. Oh no, I just get big gigabytes, terabyte. I would imagine, no, I'm not seeing anything, but I'm sure somewhere in there might be a way to do, that's some, but you can't do it on Windows 8. At least I can't, or don't know how it is, and I don't know what it's like in Windows 10. So I just went to softpedia.com and I just said, hey, Windows 7 calculator, and I just downloaded one, just to show you. So again, don't get lazy, don't use that, just use it to check your work. Alright, so why is binary important? Every computer needs an address. If your computer doesn't have an address, it actually gives itself one. And the address is a series of binary numbers. So a typical computer address is like this: 192.168.0.5. So, and that's made up of 4 bytes separated by dots. And because it's like that, it's referred to as dotted decimal format. So whenever you see an address like that, 192.168.0.5, that is an IP version 4 address. And that's typically what you see on computers today. Now, we're going to talk about IP6 later on in another video in the series. But IP6 is kind of slow to catch on. One, we have to move to it because it's bigger and we're running out of addresses on IP4. But a lot of IT guys don't do training and stuff and don't understand IP6, so they'll probably stay IP4 inside their network. So at least in the next 10 years, you're still going to be heavily dealing with addresses like this, 192.168.0.5, especially internally at companies and at company or homes, residences. Wow, that's a tongue twister. So just make sure if I ask you for something in dotted decimal format, that's what I want. I want 8 bytes separated by dots. Alright, so your computer address is just like the address on a house. Meaning, on a house, you have a home address. Let's say you live on 1313 Mockingbird Lane. Well, Mockingbird Lane is the street, so everybody on your street has the same street name. So it's your group. It's the group that you're part of, the street that you're part of. Everybody shares that. But then 1313, there's only one on that street. That's the unique part that's for you. Well, your computer address is the same thing. There's a part that's shared by everybody, the network part. Then there's a part that's unique to you, the house part, or the unique host portion. So your IP4 address, your dotted decimal format, is comprised of 2 parts, a network portion and a host portion. The network part you share with everybody else, like a street name, and the host portion is like your house number. It's unique to you. The problem is, in binary, it's a lot harder to figure out where that stuff is. So we'll be getting into that a little bit later in another video. But you need to understand binary at this moment, otherwise you can't really move on in the series. So at this point, just make sure that you understand how to convert a binary number into decimal and a decimal number into binary. If you can't, you need to stop and figure out what the problem is. Make a comment on this video. Myself or somebody else will try to help you as much as we can. So some practice. Convert 11100001 into binary. I'm sorry, from binary into the decimal. And then 00110011, convert that into decimal. And then take 185 and 27 and convert those both from decimal into binary. And make sure you check your work using the calculator. Once you're done with this part and you can get this good, you're all set to go to the next video. If you can't convert these and the number you get is different from the number that shows on your calculator, then you have an issue and you need to comment or something on the video. You can't move on. Binary is the basic building block of everything else we're going to talk about. If you can't get this, there's no way you're going to get some of the more advanced stuff. Trust me, this is the easy stuff. So that kind of wraps it up. Remember, if you have any questions, post something in the comments. Other than that, I'll see you folks in the next video.